In this lesson, we'll talk about function composition, and this topic is going to come in handy whenever you get to the chain rule a little bit later in this course. So, imagine the following scenario. You have a drop of water that falls onto a paper towel, and as you can imagine, as soon as water hits that paper towel, it begins to spread through the paper towel, probably in a circular picture. And so if we want to analyze the area of this circular damp spot, we can look at it as, well, area is pi r squared. But then the radius we know is a growing quantity. So let's suppose that the radius is given by t plus 1 centimeters. So this function is expressing how the radius is changing. And to be realistic, we probably have more than just one drop of water. There's probably a very small trickle coming in to make the radius grow at this speed. But whatever the case, what we can do is we can make a single function by taking this radius of t plus 1 and putting it in for r. That way we get pi times t plus 1 squared. This is the concept of a composite function. So a composite function is the idea of a function inside of another function. When we do this, we have an inside function and an outside function. And it's good to be able to determine which one is the inside and which one is the outside as we continue forward. But for right now, let's see if we can analyze the difference between using a composite function versus just using one function into another one. So for a here, we're talking about this formula that we found earlier. Since we found a composite function and we actually simplified it, we can plug t equals 2 directly into the function. So we get pi times 3 squared, which is 9 pi, and my units are centimeters squared. That's one way to get this. Another way is we think of it separately. We take the outside and the inside and we put them together as we go along. So the inside function is the radius. The radius at t equals 2 is 2 plus 1, which is 3 centimeters. So now we just say the area is pi r squared, and we get the same answer of 9 pi centimeters squared. So while these two look very similar, there is a slight difference going on in that one has a pre-built composite function, and the other one is using one value being plugged into another function. So let's take a look at a couple of other examples. So we've got f of t equals 2t cubed, and g of t equals t minus 3. And what we want to do is determine what these two composite functions, f of g of t and g of f of t, will look like. So, f of g of t. When we do these problems, we're always going to work from the inside out. So, at the inside, I've got t minus 3. And so now how do I take care of this? G of t was t minus 3, and let's track that as I go forward. G of t was t minus 3. And so what this means, this expression, is that this f is referring to the f of t function up here, but it's no longer f of t, it's f of t minus 3. What that means is I'm going to take this t minus 3 and substitute it in everywhere where I see a t. So, 2, t is going to be changed to t minus 3, and I always recommend parentheses when I do this. And then that t was cubed, so now t minus 3 is cubed. And notice the t minus 3 has now shown up where t was before. So, this is the answer I will take for this. Alright, g of f of t. Again, work from the inside out. So I've got g of, now we say f of t. F of t is 2t cubed. So, wherever I see a t now in the g function, I'm going to replace that t with 2t cubed. So t becomes 2t cubed, and I have a minus 3 here. So let's track it again. F of t was 2t cubed, and then wherever I saw the t in the g function, I changed it to 2t cubed. For this next example, it might not be a bad idea to pause the video for a moment and see if you can try it on your own. Okay, so if you tried this one, hopefully you managed to get something reasonable, but let's go through it. So we have f of g of x is what we're looking at for this problem. And again, work from the inside out. So g of x is 2x plus 1. And now I go back to my f function, which is e to the x, and wherever I see an x, I'm going to replace it with 2x plus 1. So I have e to the 2x plus 1. And that's my answer. How about g of f of x? Well, g is going to have e to the x plugged into it. That's the value for f of x. So, when I go into the g function, I see an x here, so I'm going to get 2, x becomes e to the x, and then I still have a plus 1. And that's the whole function. Let's see if we can do this with numbers and a table of values. So, g of f of 0. Again, you want to work from the inside out. So the first thing I'm going to do is I'm going to find f of 0. So f of 0, here's where x is 0. F of 0 has the value 3. So let me just trace this. The value for f of 0 is 3. And then g of 3, well, here's your g function. G of 3 is 6. Alright, how about f of g of 0? Well, again, I'm going to work from the inside out. So g of 0, at 0, I see g of 0 is also 0. So then f of 0 I need to calculate, and f of 0 is 3. F of g of 1. Alright, again, work from the inside out. So I want to figure out g of 1. So g of 1 is 2. And then f of 2 is negative 1. G of f of 1. Alright, inside out. So f of 1 is 1. And then g of 1 is 2. So these are all numeric problems rather than function problems, and the idea is still just work from the inside out. This last slide is probably one of the most important topics for you to get out of this particular lesson, because this is going to translate directly into what we do in the future with the chain rule. So what we're going to do is we're going to let the letter u represent the inside function, and then we're going to write the outside function in a more simple fashion by just using the letter u. So what I want to do is look at this function and say, what's something on the inside of the function? And that's going to be 4t. So let's call that my u. Well, if u is equal to 4t, what that leaves me with is y is equal to the natural log of u. And so both of these expressions are a little bit simpler, which comes in handy as we go further in the course. Let's do another one. The inside function is what's inside the parentheses. So we're going to say 2t plus 3. And with that said, y is going to be 3u squared. For the last problem, the inside of this function might not be as clear, but in general, one of the things you can use for the inside is the full exponent. So I'm going to say negative 0.22t, and then y is equal to just e to the u. And so all of these expressions are a little bit simpler than they were previously. By the way, one thing to point out here also is that these three types are generally the three types that we'll encounter in this class. You've got logs of something, you've got e to something, and then you've got something raised to a power. Although I should also point out that roots also count as powers, so roots are another type that you might see of this fashion.